credit card number, hit the buy button, and simply trust that tiny padlock in your browser. But the internet was originally designed as an open public square for academics to share information, not as a secure bank vault for financial secrets. To protect our modern transactions, engineers had to retrofit that open public square with a security blueprint built on 4 distinct pillars. Understanding these 4 pillars turns the hidden mechanics of internet security into a concrete, step-by-step process anyone can master. Let's start with the basics. A vulnerability is simply a weakness in your system, like a broken window on a house. A threat is the potential danger, like a burglar looking to exploit that open window. This table breaks down a 5-step risk analysis, acting as a systematic perimeter audit for any organization. Looking at step 4, we find the core math. You calculate actual risk by multiplying the probability of an attack happening by the impact it would cause. If you skip this structured audit, you end up wasting resources defending against the wrong threats while leaving your most valuable data exposed. Once you know what to protect, you have to secure that data as it travels. Cryptography is the process of scrambling readable information into unreadable code using a specific key. In symmetric cryptography, you use the exact same key to both lock and unlock the message. It is very fast, but you have to safely transport that single key to the recipient without anyone else seeing it. That brings us to asymmetric cryptography. Think of it like a public Dropbox. Anyone can use the open slot, the public key, to drop a message inside, but only the owner holding the private master key can open the bottom door to read it. By separating the locking and unlocking keys, 2 complete strangers can safely establish a private connection across an open network without ever needing to exchange a secret password first. We put this cryptography into action using a standard protocol called TLS. It is the engine that makes web browsing secure. This green box outlines the TLS handshake, like 2 diplomats agreeing on a secret code. Steps 1 through 3 cover saying hello, agreeing on methods, and verifying ID. Steps 4 and 5 use public Dropboxes to exchange keys securely, generating a fast symmetric session key. Finally, in step 6, the formal negotiation ends, and a shielded, high-speed connection begins transmitting your private data safely. This complex negotiation happens in milliseconds, creating a secure environment before a single byte of user information is sent across the wire. But there is still a catch. How does your computer actually know the server it just shook hands with is your bank, and not a clever imposter trying to steal your password? That requires a certificate authority. Think of them as the internet's DMV. They verify identities and issue verified digital IDs, often called standard certificates. This blue box details how those IDs use digital signatures. The sender takes a digital fingerprint of their message and encrypts it with their private key, proving exactly who sent it. By using these digital signatures, the system creates proof of ownership that makes it much harder for attackers to fake an identity or for a sender to deny their own message. Let's go back to that moment you type in your credit card and hit the buy button. In that fraction of a second, a risk protocol fired, a trusted authority verified a digital ID, and a 6-step handshake used 2 types of keys to build a secure tunnel. The servers handle all that complex math for you. But you still have to protect your end of the bridge. This best practices list outlines your job. You must verify that your connection is secure, use extra login protections like multi-factor authentication, and keep your software updated to close those broken windows. Internet safety is a logical 4-pillar blueprint. And now you have the exact framework needed to understand how it keeps our world connected and protected.